In order to do the problem, you have to understand the problem. Let's read it. Sand is falling from a rectangular box container whose base measures 40 by 20 inches at a constant rate of 300 cubic inches per minute. So let's make sense of what's going on right there. Let's see. I want to move this up, and then I got this. Okay, so it's pouring from a box. Let's draw a box. This is a box right here. There's sand pouring out of this box. It's 30 or 40 by 20, so I got 40 right here, and it's by 20. And then it's flowing out at 300 cubic inches per minute. Is it minute? Yeah, per minute.
Yeah.
Inches a cube per minute. All right. So the first question says, how's the depth of the sand in the box changing? Well, if you had sand in here, how would it be changing? It would be going down. The depth would be going down. The depth would be however high the sand is. So if the sand was right here, this depth would be going down. So we know that our answer is going to be negative. Now, what do you guys want to use for the depth of the sand box? Let's see. I don't want to use H or D because I know in the future we're going to need it. Let's just do S, shall we, for sand? Yeah, that sounds good. So, how is the depth of the sandbox changing? That's going to be, we're going to call them ds over dt. So we're looking for ds over dt. I don't like that. Let's use H. I don't like S. Okay, so dH over dt. So that's going to be the height of the sand. Yeah, I like that. Okay, so how is that changing? Now, is there an equation here that we know of that has an H inside of it for this box? Let's see. This is exiting. Yeah, volume. Hey, that sounds good. The volume equation is going to be base times height, or base times width times height, right? So base times width times height, and that's your H. There it is, people. Okay, but wait a second. Is the 40 and the H, or the 40 and the 20, the base? Oh, it's length times width times height. That's what I'm used to. Let's do that. Let's do length. My length is 40. My width is 20. Is the 40 and the 20 changing during this process? As the sand is pouring out, is 40 shrinking or growing, or is 20 shrinking or growing? Like the box, the shape is actually no, it's not. The shape is not changing. The only thing that is changing is the H. And so, before you take the derivative of this, let's plug in the L and the W, because those are constant numbers. They are not going to change. So we have 40 times 20. Then we have our H right there. This equals V. So we got V equals, what is that? 800, and then height. All right, so now let's take the derivative of this with respect to time. So when I take the derivative of this with respect to time, let's see, d over dt, I get dv over dt, and that equals, what's the derivative of h? Oh yeah, for this case, it's just 800. And then we have dh over dt. Oh, no problem. Not bad at all. Okay, so do we know, because right now we have two variables. We have dv over dt and dh over dt, and dh over dt is what I'm trying to find, so do we know what dv over dt is? Yep. The sand is pouring out at 300 cubic inches per minute, so we can put 300 there in place of dv over dt equals 800 dh dt, and we get our answer. dh dt equals 3 over 8, because you would divide both sides by 800 and you got your answer. So now my answer is still wrong. Everything was right up to this point. If I leave it like that, it's still wrong. Why is it wrong? Yeah, because it's decreasing. It should be a negative rate. How come I didn't get a negative number? Well, actually, probably because I didn't put a negative on the 800. I could have put a negative on the 800. No, not the 800. The 300. Because the 300 is the rate at which the sand is exiting the box. Right? Okay, let's take a minute and take that all in. Thank you, Nico, for that. I almost forgot my label here. The inches per minute. Because this is a measure of the length. H is a measure of length, so we just keep it as inches. Alright, so the next part says the sand is forming a conical pile. There's the conical pile, cute little picture. Sand is pouring out, and we have a conical pile right here. At a particular moment, the pile is 23 inches high, and the diameter of the base is 16 inches. The diameter of the base at this moment is increasing at that 1.5. I don't like using decimals. I'll change it to a fraction in a minute here. Inches per minute at this moment. Okay, period. At this moment, how fast is the area of the circular base of the cone increasing? Let's find out. Alright, first I want to circle some important things here. We got inches, we have that formula, we have this guy right here, we have this guy right here. Now this is a rate, so that's very important for me to note. What is that rate? The diameter of the base at this moment is increasing. So the diameter, so let's go dd over dt. Okay, the second d represents diameter there. And then this was the diameter, so that's what d equals. Let's say d equals that. And then what's that other number? 23. That's high. That's another h. Oh, I hate using h inside the same problem, but since this is like the b and this is a, I'm going to use h anyways. So h equals 23, d equals 16, and dd over dt equals 1.5. How fast is the area of the circular base? So there's a hidden equation here that would give us a starting point to find out how the area of the base is increasing. What is that? What is that secret equation, the hidden one? I mean, if it wants to know this, then it wants to know dA over dt. Right, right. So give me an equation with a capital A. Capital A is the area of the circle. So we're going to say pi r squared. All right, now I'm going to stop right here. And don't write right now. Don't write. I'm going to take the derivative of this. I get dA over dt, and on the left side, I drop the 2 to multiply to the pi. The pi is a number. It's like a number 3. And if you were to take the derivative of r, you would multiply that 2 to the 3. So that's what I'm doing right here. And then we have r, then we have dr over dt. Now, there's a problem here. We're trying to find a, dA over dt. That means we need to know what r is, and we need to know what dr over dt is. Do we know what r is? Yes, because the diameter is 16, which means the radius is 8. Okay, do we know dr over dt? No. We know how the diameter is changing, but we don't know how the radius is changing. Well, can't you just half that? No, you can't. I guess the most simple layman's way for me to explain that is if I had a circle right here and I had a radius that was increasing, it would only be increasing this way. But if I had a diameter, the diameter would be increasing this way and this way at the same time. So you can't really just half the rate at which it is changing to get the same answer. Okay, so how can I rewrite this so I don't have an r anymore? I don't have a dr over dt, but I do have a dd over dt. Is diameter related to radius? Oh, heck, yes it is. Instead of writing radius, we can write 1/2 d squared. Oh, snap. And notice how I wrote 1/2. I didn't say d divided by 2 because I don't like fractions. I don't like when my variables are in fractions. I think it's easier to see this way. So, my students, what is 1/2 d times 1/2 d? 1/4 d squared. D times d is d squared. Very beautiful, very nice. Alright, so let's write this a little differently, and then we'll take the derivative of it with respect to time. We have pi over 4 times d squared. Let's take the derivative of this with respect to time. That means we're deriving implicitly. The derivative of a is going to be 1, but then we would have to multiply by a prime, so we have dA over dt. And on this side, we're going to drop this 2 to multiply to pi over 4. And, ooh, what would that be? Let's just write it out. 2 times pi over 4. Then we have d, and then we have times dd over dt. I put the 2 over 1, and that 2 would cancel out with that 4, so I'm left with pi over 2 d times dd over dt. Now we were looking for dA over dt. So do we have the other numbers? Do we have a d and do we have a dd over dt that we could plug in? Yeah. All right, so we have, what is this, a 16? And then this would be a 3 over 2. Where'd that come from? You see this 1.5? I'm changing that to 3 over 2 because I don't like decimals. This is what dA over dt is. Let's cancel some stuff out. This 2 goes away. This becomes an 8. This 8 goes away. It becomes a 4 because of this 2. Now I have 3 times 4 times pi. So dA over dt equals 12 pi. Oh, this is area, right? So inches squared per minute. Don't forget that label. Okay, I'm going to move this up more, but I want you guys to remember this guy right here because we're going to need him. See this right here? It says, how fast is the height of the pile increasing? The pile, what's the shape of this pile? Oh, it's conical. Oh, there's the formula to find volume. Oh, there's an H. All your stuff is right there. Okay, so I'm going to move this up so we can see it. All right, here we go. We got V equals, I think it's 1/3 pi r squared h. Is that right? Is it pi over 3? Oh, yeah. Well, that's the same thing. Let's put the pi on top of it. I like that too. Pi over 3 r squared h. All right. Now, can I just plug in what the r is right now? Because I mean, all I'm trying to do is I'm trying to find out how is the height of the pile increasing. I want to know what dH over dt is. That's what I want. So does that mean I can plug in 8 for the r? Because it said the diameter was 16. Can I just plug in 8 right here? No, you can't. Because it's changing. The r is changing. If the r was constant, like our friend the box earlier, like you remember how the sides were not changing on the box? So if the sides aren't changing, the number doesn't change, then you can plug it in. But because r changes, you don't want to plug it in. And we don't have a dr over dt, do we? No. We have a dd over dt, so let's get rid of that r and put in our cute little diameter substitution. So we have pi over 3, and we have 1/2 times d, and that's our new r, so we got to square him. Let's simplify this before we take the derivative, shall we? Because if you don't, it's going to get dirty really quick. All right, so 1/2 times 1/2 is 1/4, and 1/4 times pi over 3 would be pi over 12. And then we have a d squared, h. All right. I know I'm going a little fast with the arithmetic, but we got to get to it. All right, so if I'm taking the derivative of this, I have this function multiplying to this function. So we definitely have the product rule to do. So we have dv over dt equals, all right, take the derivative of this first dude right here. We drop the 2, we multiply it to the pi over 2, or pi over 12, and you would get pi over 6. I don't want to skip any steps. I want you guys to be able to follow me. 2 times pi over 12. Then we have d, and then we have dd over dt. And then we have to multiply it times the other function, which is an h, so the h is going to be chilling with him. Then we have a plus. Now let's take the derivative of this h, but first let's write the first function. When I write the first function, it's going to be pi over 12. And then we have, pi over 12 d squared. And then the derivative of h is 1. Then we get a dh over dt, which is our prize. That's what we're looking for, dh over dt. Hello, dh over dt. I've been watching you. Well, that's weird. All right, dv over dt equals pi over 6, because this 2 is going to cancel out with that 12 and make him into a 6. We divide the top and bottom by 2. And then let's plug in stuff at the same time. What is d? It is 16. All right, so I'm going to write 16 like this. I'm going to put them over 1 because I have a feeling I'm going to be cross-canceling some stuff later. Let's see. If you didn't know that, you would just write 16. You would write like that. And then, let's see, what's next? Oh, yeah, dd over dt, and that was, as a fraction, 3 over 2. And then we have the height. Do we know the height right now? Yeah, it's 23, people. Come on. You act like you didn't even do this problem. Pi over 12, and what is d? It is 16 squared. And then, I'm not going to write that one. And then I'm looking for dh over dt. Oh, man, I have a feeling this is not going to look pretty when I'm finished. Now let's start canceling things out, shall we? We shall. All right, let's start out with this 16. Make it into a fraction. I have this 16 and this 2. That 2 becomes a 1. The 16 becomes an 8. I see this 6 and this 3. The 3 becomes a 1. The 6 becomes a 2. Oh, look at this 2 and this 8. All right, man, look at all that simplification. I like that. Now we just have 4 times 23. Pretty. Pretty, pretty, pretty. All right, so 4 times, that'd be 92? 92 pi. You thought we forgot about you, pi. Oh, snap. Do we know what dV over dt is? How is the conical pile increasing the volume? Like, how's the volume increasing? It's increasing by 300. Oh, snappity waggity daggity. Okay, now over here, whoa, we got some more work to do. I'm not going to look at this squared anymore. I'm going to look at 16 times 16. Now, can I simplify that? Because I don't really want to multiply 16 times 16. I don't have a calculator handy. And I can do it long ways, but who wants to do that? Divide this by 4, we get 3. Divide this by 4, I get 4. Ooh, that's nice. All right. Okay, so now I have 4 times 16. It's going to go up there with the pi. 4 times 16, what is that? That's 40 plus 24. It would be 64 pi. And on the bottom, I have 3 times nothing. Okay, so I have 3 right there. And then this is dH over dt. Let's get dH over dt alone. Okay, so we have 300. I'm going to subtract the 92 pi from it. So this, to the other side. And then I'm going to, let's just write it out. I don't want to lose you guys. Maybe I lost you already. I don't know. dH over dt. Okay, now how do I get rid of fractions? Multiply by the reciprocal. So if I multiply that by the reciprocal, that means this is going to be a 3 up here, and I'm going to have a 64 pi on the bottom. Don't even think about simplifying that, nasty dude. Okay. Oh, but let's do, what's the label here? How fast is the height increasing? Okay, so that's an inch per minute. Man, that's disgusting. All right, but it's done. Someone asked if the 300 should still be negative. That's a good question. Now, remember earlier we were talking about the box, and the sand was exiting the box. And so, therefore, the volume of the sand would be going down inside the box. But here we're talking about the cone, and in this conical shaped pile right here, the sand is actually increasing. And so, no, we want to keep that positive. Good question.